Okay, this begins video 2 for the chapter on wind power. So let's go ahead and start this video with an example problem. This is an example problem from your book, and the example problem reads, a 27 mile per hour wind at 14.7 psi and a temperature of 70 degrees Fahrenheit enters a two-bladed wind turbine with a diameter of 36 feet. And it's asking you to compute the following. The power of the incoming wind, the theoretical maximum power that can be extracted, a reasonable value for attained power, and the rotor speed in RPM for part C, as well as the torque for part C. So let's go ahead and start with, excuse me, with the available power from the wind. From earlier, we went ahead and derived that available power will be 1/2 air density times sweep area times wind speed cubed. Now, in order to get the air density, we can use the ideal gas law. And actually, we can recast the ideal gas law by dividing through by specific volume. So we end up with P equals rho RT. We can compute what the density is by taking the pressure and dividing it by the gas constant times temperature. So the pressure, again, is 14.7 psi. We'll multiply that by 144 square inches per square foot. The gas constant for air in English units is 53.58, and again that multiplied by the air temperature in Rankine. That gives us an air density of 0.075 pounds per cubic foot, and we go back up and we can plug in all those numbers, that number into the equation for the power. With 36 feet, we get, again, pi over 4 times 36 squared. Again, that would give us 1,018 square feet for the sweep area. And then the wind is 27 miles per hour. And again, we do our conversions. We have 5,280 feet per mile, as well as in 1 hour, there's 3,600 seconds. We go ahead and bring that to the third power. We can, again, using our proper conversions, get this into kilowatts, 100 kilowatts, or 134 horsepower for the total available energy in the flowing air. Now, part B is asking for the maximum power extracted, and that's simply just basically taking the Betz limit. Excuse me, go ahead and cross out that little error there. You can take the Betz limit, which is 0.5926, multiplied by the power available in the air, which is 100 kilowatts. That gives us a total of 59.3 kilowatts for the max power. Okay. Now moving on to part C. Part C is interesting. It's asking for a reasonable value for obtained power. The only way I can think of getting a reasonable value for obtained power is to go back to this chart. Now it says that it's a two-bladed wind turbine. So if I look at the two-blade wind turbine or the two-blade Darius model, the maximum power extraction, at least not according to Betz limit, but according to its performance, is just slightly above 0.45. That's for this for a wind tip speed of advance ratio, sorry, of 11 for the high speed version, and a Darius version that gives us a wind tip speed of a little over 6. So My take would be is let's just go ahead and assume the power coefficient to be 0.45. And again, this is for assuming a high-speed two-bladed wind turbine, according to the graph performance that we looked at before. So the power extracted would be 0.45 times the available power, which is 100 kilowatts. So we can probably expect about 45 kilowatts or 60.3 horsepower. Now, part D is asking for the rotor speed in RPM. So if we go back, again, about 0.45 here, 0.46 if you want to be exact. If we go down, we get an advance ratio of 11. So if we come back here, if we look at for a power coefficient of 0.45, we have an approximate advance ratio of 11, which is the tangential speed over the wind velocity. Now, the wind velocity in the problem statement was given as 27 miles per hour, which, if you convert that to meters per to feet per second, is about 40 feet per second. So if we saw this equation for angular speed, we get advance ratio times wind velocity divided by radius. Excuse me. So if we go ahead and plug in our numbers, 11 for the advance ratio, 39.6 feet per second for wind velocity, and the radius is going to be half of 36. So we get, with the proper conversions, a rotational speed about 24.2 hertz. So if we were to go ahead and take that to convert it into RPM, basically 1 hertz is equal to 60 RPM. So we have 60 RPM divided by 1 hertz. So if you do the math, you should get an RPM speed of about 1452 RPM for this particular turbine. And then part C, I'm sorry, not part C, part E. Part E is asking for the torque. So again, the torque in this case would be just the actual power extracted divided by the angular speed. So here we'd have power extracted is 60.3 horsepower. We can convert the horsepower by taking 550 foot-pound per second in 1 horsepower. Divide all of that by the angular speed in hertz. You should get a torque of about 1370 foot-pounds. So those are just some performance criterion for this particular wind turbine. Now, we looked a little bit into wind turbines. I'm going to take some time at this point to talk a little bit about wind speed. So let's look at some wind energy resources. As you can probably imagine, wind speed is very variable. It's not constant. So wind data has been collected and is available at the National Renewable Energy Laboratory website. So this basically, the data is presented as a wind energy atlas of the United States. Basically takes the wind and rates it according to the degree of uncertainty of what velocity it's going to be blowing at. 1 with the lowest degree of uncertainty and 4 being the highest degree of uncertainty. And then it looks at wind in terms of what we would call a wind power density distribution. So you would basically use this atlas to look at possible candidate locations by looking at the available wind power per meter squared of wind turbine area. So it helps you to kind of get an idea of how much energy you can expect. Wind itself is rated in classes of 1 to 3, and those classes are specified at either 10-meter or 50-meter locations. So example, you can see on this table, you have the 7 different wind classes, right? And that gives you the wind power density and the speed at 10 meters and at 50 meters. So for example, class 4 wind gives a power density between 200 and 250 watts per square meter and a wind speed between 5.6 and 6 meters per second. This is a map which gives the United States annual average wind power density. So the darker colors mean higher wind class. Wind energy is appropriate for class 3 or above. And those areas can be mostly found in uh, coastal areas and in the Midwest. These numbers is looked at in terms of a probability of occurrence of a specific wind speed. And those are expressed in terms of something called the Weibull distribution. The Weibull distribution just basically gives you the percent of hours per year per mile an hour as a function of wind speed. So you can see, for example, this curve increases to a certain velocity, wind velocity here of about just under 10 meters per second. And that would basically represent about 11.5% of the total hours per year that wind speed's occurring. So it's used as a way to try to, again, quantify the amount of wind energy available. So this Weibull distribution is a basic probability function that's used to quantify the amount of energy available by wind. Okay, let's look a little bit more into the specifics of wind turbine operation. And I'm going to do this in terms of asking two questions. One question is going to be, what should the operating strategy be for a wind turbine as a function of wind speed? Right? So you have a specific location that has variable wind speed, right? It goes from no breeze up to a certain high-end wind speed. And those wind speeds are occurring at different times over the course of the year. So how do you size the wind turbine, right? And what's the strategy for it? Well, one thing is that you are not to operate the wind turbine at its maximum power coefficient, right? So you don't want to pick a turbine that is so big that the wind only hits that point for such a short time a year to actually get that much energy out of the wind, right? So the question is like, why not? Why wouldn't you not? Why not operate the wind turbine at that? Well, there's a few answers to that question. One is that operating at that maximum power coefficient for all wind speeds would of course, maximize the energy extracted, but factors such as generator capacity and structural components and safety would be an issue. And also, sizing a generator for an input corresponding to the maximum speed range would result in that generator being oversized for the majority of the year, and you only be actually using the maximum capacity of the generator for the short time that those maximum wind speeds are occurring. We're going to look a little bit more into that in the next several slides. Before that, I just want to take a quick look into the interior of a nacelle. So this is again where the turbine and generator are encompassed. So you have in here a generator, a gearbox to convert the low shaft speed into a higher speed shaft going into the generator. You have a yaw motor and drive to basically keep plane of the blade oriented towards the wind. You have a pitch mechanism, which is pretty cool. It's a pitch mechanism that basically orients the attack angle of the turbine blades as the wind speed changes to either try to slow down the wind turbine a little bit if the winds are going too fast, or to increase it. And then you have a brake, which is a safety precaution to slow down the rotor speed entirely if need be. So again, you have orientation where the wind turbine is being shifted to point towards the wind. You have a pitch mechanism here on the turbine on the blades, I'm sorry, in order to shift the angle of attack between the wind and the blades. And then you also have a brake to slow down the overall speed of the turbine. And that brings us to this graph, which I wanted to take some time to explain. This is what I would call a control strategy for a wind turbine. So here on the y-axis, we have percent generator output, and on the x-axis, we have wind speed. So I'm going to take some time to explain how this performance curve works under the basic control strategy. So again, between, let's say, 0 and 5 meters per second, the wind turbine is not spinning, right? You haven't hit the minimum velocity in order for the wind turbine to start turning. Then, a little after 5 meters per second, we start extracting power. This is an area called constant power, or constant power coefficient regime, right? So between this point and this point, CP is constant. It doesn't look like constant because I'm like, how could it be constant if you're increasing in power extraction? Well, remember, the power extraction is divided by the total power in the air coming to the turbine, and that is a function of the wind speed. So this is as wind speed's increasing, you're in the constant power region. Now, in this constant region, the turbine extracts the maximum power from the wind, but the power extracted is less than the rated input to the generator, right? So again, this isn't constant power extraction. You're constantly extracting the maximum power that you possibly can. Until you hit this region, which is where you've hit 100% of the generator's capacity. So now the control mechanisms in the turbine are trying to slow the turbine down. So what happens now is that power extraction is constant. So this part is constant, but the power in the air is increasing, right? So that you're extracting the maximum power that you can, according to the rated generator, but the power of the air, the wind coming in, is increasing in strength as the air velocity is increasing. So what's happening is that your actual coefficient, your power coefficient, is decreasing, but your power is constant. Until you hit a point when the wind speed is getting dangerously high, and at that point, the brakes kick in, and it just stops the turbine from spinning altogether for safety reasons. Okay, thank you. At this point, I'm going to end this video, and we'll continue this chapter in the next one. Thank you.